Hello, my name is Zachary Smith and I am at Ohio State University, and I will be discussing the influence of lithology and pre-existing damage on brittle fragmentation during dynamic tensile loading. I will begin by discussing the motivation and background for studying dynamic tensile fragmentation and then discuss our experimental methods. I will follow up with our results, which first include mechanical data and digital image correlation. Then I will compare the influences of lithology and pre-existing damage on tensile fragmentation. Finally, I will discuss the implications of this research for fault zone development during earthquake processes. Field and modeling observations suggest that isotropic tensile loading may be a viable mechanism for producing pulverized zones along large strike slip faults. However, the influence of lithology and pre-existing damage on these processes is still poorly understood. We use a modified sample configuration for a split Hopkinson pressure bar, which consists of two lead discs bonded to an inner rock disc. When this sample configuration is loaded axially, radial strain in the lead drives isotropic tension in the inner rock disc. By analyzing mechanical data from the split Hopkinson pressure bar in comparison to high-speed photography and digital image correlation, we can determine the tensile strength of the rock. In Figure 5, circumferential strain is plotted through time during a layered tension experiment, and you can clearly see fractures initiate and propagate through the rock sample during the experiment. In Figure 6, we compare tensile strength for westerly granite and Berea sandstone, where tensile strength is plotted as a function of strain rate. I want to point out that there is a zone between strain rates of 10 to the first and 10 to the second per second where tensile strength becomes strain rate dependent. But this inflection point changes based on lithology and is different for westerly granite than for Berea sandstone by about a half order of magnitude. Analysis of damaged fabrics shows that crystalline rocks fell through polygonal fragmentation and there is no preferred fracture orientation. In comparison, granular rocks fell through the formation of dilation bands and distributed pore space expansion. In Figure 7 and 8, photomicrographs show this deformation up close. In addition, we evaluated the influence of pre-existing damage on tensile fragmentation in Berea sandstone, and we are currently working to do so in westerly granite, but do not report those results here. In order to test how pre-existing damage influences dynamic tensile fragmentation, we implemented a series of heat treatments on Berea sandstone. In Figure 9, we show the change in physical appearance for heat-treated sandstone, and in Figure 10, we show the change in rock properties due to heat treatments. In Figure 11, we compare fragment size for each heat treatment level to tensile strength, strain at failure, and strain rate at failure. Fragment size appears to decrease with increasing tensile strength, but we are still evaluating these early results in order to understand these processes further. Our results suggest that dynamic tensile loading along bimaterial fault interfaces may produce dilation bands and distributed pore space expansion in granular rocks and tensile fragmentation with no preferred orientation in crystalline rocks. However, post-seismic contraction due to lithostatic pressure would likely erase evidence of dynamic isotropic tensile loading in granular media, which could explain why we do not see widespread pulverized zones in granular materials in the field. In conclusion, our results suggest that tensile fragmentation is a viable mechanism for pulverization tens of meters from a fault. And our results serve to explain variations in damage based on lithology and pre-existing damage. I would invite you, if you have any questions, to contact me. And at this time, I'd like to thank you for your time.